So Ludovic has had a really interesting career in robotics. He got his PhD from EPFL, and then he did a postdoc with Stefan Scholl at USC. And then he moved to Max Planck, where he was a group leader for several years. And now he's moved to NYU and still holds a joint appointment at Max Planck. And Ludovic's work is in humanoid robotics, dynamic locomotion, multi-contact motion. So really kind of pushing the edge of what you can do with humanoids today. He's won several awards, the IEEE RAS Early Career Award, as well as the European PhD Award, and an IROS Best Paper Award. So he's been quite accomplished in his work. So let's all welcome Ludovic Righetti.
Thank you. All right, thanks Dimitri for the kind introduction, and thanks everyone for being here. I'm actually very excited to be here. Last time I was here, I was still a grad student. It was in 2006, so yeah, it's nice to be back. Yeah, okay. So what I do in my lab, I'm interested in things like that. Say, how do we accomplish tasks that kind of everyday tasks, right? Nothing crazy, but doing. I mean, maybe this is already difficult. If you look at different types of tasks we achieve every day, or if you look at what animals are doing, it's all about interacting with the world, right? Or everything that we do, it's all about how do you interact, how do you basically touch things, and how do you, in humans or animals, we can touch things and we never break anything, right? I mean, we break things, but things are always really nice. And that's in stark contradiction with what robots are capable of doing, right? Robots are really good at not touching anything. Each time they have to interact with something, usually things become very difficult. And this difficulty somehow doesn't really exist for people, right? So I see that every morning, right? In New York, interacting is not an issue, right? There's never a moment where you basically need to spend an hour of computation to decide how you're going to do anything. Even the most mundane thing, right, is about interaction. Even if you want to sleep, you basically need to interact with something. So how do we do that? How do we compute those things? How do we reason about those things from an algorithmic point of view? That's the kind of things we try to look into my lab. And it turns out that it's very difficult. And maybe beyond just this idea of, okay, humans do that, it's great. Why does it matter? Well, it matters because if you look at things like that, so I don't know how much you know about so I didn't know much about the aerospace industry until I talked with people at Airbus. How much automation do you think there is in when you build a plane? I don't know. So for a car, there's a lot of automation to build a car. I guess here you know more than I do actually. There's a lot of automation to build a car. How much in a plane do you think?
Well, how do you measure that? We're trying to figure out how to.
So how many?
67%.
No, so actually it's easy. There's none. All of the assembly of the plane is done by hand. So you don't have robots that actually assemble a plane. So you can build some subparts in a chain, in the manufacturing chain. You can build things on a chain, right? But the moment you need to assemble these things, actually there's no machines that do that. It's all made by people.
They build the wings in one part of Europe. They build the tail in someplace. They bring them all together.
Yeah. I think that's what they do, yeah. So they can, I think subparts, they can automate the manufacturing to some extent, but the moment you want to actually assemble these things, it's all done by people. There's zero automation because you need to, basically the problem is that you need to get inside the plane. And we don't have machines that can go inside the plane and with a form factor that is such that you don't have to redesign your plane. And the big deal is that you actually, the moment you get inside the plane, you need to interact with the environment that you don't necessarily know a priori. You need to be able to manipulate tools. You need a form factor that is nice with the plane, right? You cannot redesign the plane to shape these big industrial robots that we have that can have the precision that you want. And so, for example, they're very interested. So how do you get robots into that? How do we automate this? And one of the things that we need to be able to reason about. Mobility, so locomotion, and manipulation at the same time, and we need to do that in a way that deals with these kind of environments that are actually complicated environments, because to get into the plane, in the wings, you need to actually crawl as a human inside, right? You cannot just walk on a flat ground type of thing. So that's true for a plane, but it's true for a lot of most of the industries, right? If you look at construction, how much automation in construction is pretty much nothing, right? It's all made by people. A big deal of it is made by people. And yeah, so people in construction always say that their technology is pretty much 100 years old, right? A lot of things that they do is still done by people. But it's true everywhere, right? If you look in a kitchen, there's no automation virtually. In maybe disaster sites, again, we start to have drones that can go and do surveillance and do monitoring, but we don't really have a lot of machines that go inside and help people, right? We're not there yet. And then you can think about applications of this. If you understand how motion should work, I'm especially interested in leg locomotion, these are the kind of applications that it makes a lot of sense to start thinking about multiple contacts and leg locomotion. If you understand that, hopefully you can also design prosthetic feet. So it's still a dream, right? We're not really there yet. We don't have these kind of things. So now you might argue, say, okay, but there's a lot of people who do walking much better than I can do in my lab, and so that's an example of maybe that's the best robot that exists today that can do things, except that when it goes into interaction in a way that is not expected, things don't go very smoothly, right? And I do not mean to make fun of Boston Dynamics, because I think they do things that I cannot do in my lab, right? They are really amazing, but still it's a problem, right? It's not a solved problem. It's not that people have figured it out. Understanding how you can use contacts and how you can not only use contacts, but how do you reason about them and maybe use them to do something interesting. So that's the kind of things we try to do in my lab, is say, how do we do that? And how do we do with motion? How do you get robots to move? And how do you get robots to interact with the world? And there's two things we looked at. We tried to look at physical models and basically formulate these problems as optimal control problems, try to solve them efficiently. And then we look at data and try to say, can we learn things that we don't know how to model very well? And ideally, we want to do both at the same time. And that's basically the general idea of what we do in my lab. So I won't show you everything that we're doing. I want to show you three things that I find are kind of interesting. We've done some work on optimal control of multi-contact locomotion. So how do you use your hands and legs and multiple whatever things, part of your body to cross complicated terrains, and how do you do that in very fast? How do you learn, for example, tasks that involve very high impact dynamics? Can you use data to do that? And the last thing is it's really based more on the reinforcement learning part. So how do you basically design control strategies that will allow you to learn a better model faster? So how do you at the same time try to control and explore your space so that you can learn models faster when you do reinforcement learning? So that's the three things I would like to show you today. So the first thing is optimal control of multi-contact locomotion. So what do I mean by that? So I mean that assume you want to do something like that. What does it entail if you want to plan that? So what you need to figure out is that you want to compute where you want to put your hands, where you want to put your feet, and which sequence you want to do that. Then you need to figure out how much force you want to apply at every end effector, right? What is the change of force over time? Most important, you want to figure out what your center of mass is going to do, or the angular momentum of the system, right? That tells you globally how you're moving. And eventually what you want to figure out is what should the entire body do in sequence in order to be able to achieve that. And whatever you compute needs to be consistent with the dynamics of the robot. So it means that whatever desired motion, desired controls that you do needs to be satisfy physics. So we use models of rigid body dynamics models, say that mass times acceleration plus all the forces that you're modeling is equal to actuation plus contact forces, right? And you have Jacobians that just maps things in the general coordinates. And the other problem is that you're not allowed to choose arbitrary contact forces, you're not allowed to choose arbitrary torques, and you cannot choose arbitrary position, velocity, accelerations. They're subject to bounds, right? That says basically what maximum joint limit, maximum actuation limit, and friction cones, for example, that search that you don't sleep, or if you sleep, that you can control the sleep and you know what you're doing. So optimal control problems say, how do you basically optimize controls over time such that these things are correct, right, or satisfied. It turns out it's very difficult because first, if you want to look for where you put your feet and your hands on the ground, in which sequence you have a combinatorial problem, and it's it's not very tractable if you don't make assumptions. So we have actually here a specialist that knows how to do that really well. But that's first, that's a problem. But let's assume you can do that. You still have problems because you have a non-smooth dynamics, right? When you have impact, your model is changing depending how you model your friction. you have very high dimensionality because we are not talking about one rigid body. We're talking about if you have a humanoid or a leg robot, you maybe have 30, 40 degrees of freedom. The prime is not convex. So not only is hybrid, but it's not convex because dynamics is not convex. The constraints that we have are not convex. So it means that you cannot find a global solution easily. You need to make approximations. And the strategy that we take, and we are not the only one, is to say, can we exploit the physics, the structure of the physical problems, such that we can break it down into meaningful problems that we can actually solve quickly. And that's what I would like to show you today. So the typical problem is that we're going to usually people will assume that we have a reachability or contact planner that will decide what is the sequence of contacts I need to create, which means first I will decide if I need to move my left leg first, and then I use my hand, maybe use my other hand, and move my other leg. So this tells me what is the sequence, and I assume I have a planner that can do that. So Yoshi that is here knows how to do that, so we assume we take his planner, he gives us a solution that is great. After we have that, what we want to do is can I find a dynamically feasible motion for the entire body? So dynamically feasible means that I can compute contact forces and the motion of the entire body such that it satisfies the equations of motion. And finally, I assume that I put this into a controller that is going to optimally make this happen and track whatever things I've planned over time. So that's the general idea, how do you decompose the problem? And what we go and try to go beyond that is say, let's look at the dynamic feasibility problem, and let's see what we can do there to make it even better. Because if you just try to optimize this problem, so assume you have contacts, you try to optimize with the dynamics equation I showed you before, if you just don't think about it, it's going to take you hours or days to actually find a solution that makes sense. So can we make this faster such that we can go close to real time? And the idea is that we found a way to decompose this problem such that we can actually do that really fast. So go back to the equations of motion. So I don't know how many of you are actually familiar with well, first that and basically optimal control problems in general. Okay, so I don't. Okay, so I can move a bit faster. Just interrupt me if what I'm saying it doesn't make sense. So the idea is that okay, that's the general equations of motion. So what is nice is you can split them in two. You can look at the unactuated and actuated part of the equations. So the actuated part is just the part where the actuation shows up, and here this is where there's no actuation. If you look at a bit more details, the unactuated part is just 6-dimensional. It just describes the change of momentum of the system. So it's the linear and angular momentum change of the system. So you can rewrite it in a different way. You can just say the rate of change of momentum is just equal to the sum of forces for the linear part and equal to the sum of moments for the angular part, right? So basically what it means is that the unactuated part tells you how the interaction forces move the center of mass pretty much and the angular momentum. So you can reduce, this dynamics reduced to basically the dynamics of a stone, right? One body, that's it. And what's left is the rest of the body, right? Everything else. And it turns out that this is just the equations of a manipulator. So you can see that for any combinations of these other accelerations of contact forces, you can find basically a torque that satisfies that. So what it means is that if you assume that you have enough torque in your joints, this problem is just a manipulator problem, and you don't have to care about dynamics here. The only thing you need to care about is kinematics. Can you actually move your hand to the contact that you want to go to? Everything else does not matter. There's no dynamics involved here anymore, because if you have enough actuation power, you can always satisfy this equation.
You're
right?
assuming you can measure lambda?
No, I'm assuming that I'm going to plan for it. And then I assume that I can control it, yes. But I assume that if my contact model is good enough, I will be able to control it. Yeah. So now the idea is that if you look at this problem this way, then you have basically a natural way of solving this problem. Say, first, let's optimize the momentum equations and find a series of contact forces that allow to move my center of mass from A to B, and then optimize the kinematics such that it actually happens. And if you do them together and they agree, then you're done, you solve the entire problem, right? So that's what we do. We start with the kinematic optimization. We say, let's optimize the kinematics of the robot. Let's assume I want to go from A to B. Kinematics optimization just says, well, if you want to go up, you just move your legs such that you touch your contact points when you want to touch them, and you move the robot there, right? So here you see that this is not something that is feasible. I don't know if it's clear for everyone, but you will not be able to do that on a robot because you would fall, right? Because the center of mass, for example, is way too on the side. In order, you would be able you would need to actually push pull here instead of pushing against the contact if you wanted to go up. So this is not feasible, right? But it's a first guess. So the idea after that is that we're going to solve the dynamic optimization problem. It's just saying finding contact forces and contact moments that minimize a certain performance cost. I just say I want to move my center of mass from A to B. And what I do is that in addition, I give to this optimizer an additional cost that say, while you do that, try to not be too far away from what the center of mass was doing when the kinematic optimizer was optimizing that, right? So you try to find a solution that is dynamically feasible, but is not too far away from the what the kinematic was doing. Then you get a solution, then you put it back into the kinematic optimizer, and you say, re-optimize the kinematics, but this time, try to not go too far away in terms of what the center of mass is doing. That's the only thing that we look at, and the angular momentum. That doesn't go too far away from what the dynamic optimizer was doing. And if you do that a few times back and forth, so we can actually not prove it, because in practice it works very well. After two, 3 iterations, usually we find a consensus, and then we have a solution to the entire problem. And this is how it looks like. Now we found a solution that is actually dynamically feasible, right? So you can go up, and the entire body motion is actually doable. What is nice with that is that actually the kinematic optimization problem is easy, right? We know how to deal with kinematics in robotics, so we can really do that really quickly. And the dynamic optimization problem, well, is very low dimensional, so we can do that really fast as well, right? So it turns out that you can do the entire thing really, really fast. So that the dynamic optimization, I call it the central load dynamic optimization, because the central dynamics is basically the change of momentum if you look at it from the center of mass point of view. So we looked into that into more details. So it turns out this problem, I say it's easy, it's not that easy. And the problem is that why it's not that easy is because, so we're going to assume this is an optimal control problem, and we're going to assume that our optimal control variables, or control inputs, are the contact forces. So we don't have access to that, right? We assume we will be able to generate them afterwards, but we assume we can choose them. We can assume we can choose them arbitrarily. And we're going just to say, I'm going to choose them arbitrarily, but I'm just going to make sure that they stay within friction cones, or they're basically satisfy my contact model, right? The difficulty here is that I have a cross product. And because I have a cross product, this problem is not convex anymore. So the cross product basically so I'll show you a picture afterwards. It basically makes the problem, so you have a constraint that is basically looks like a quadratic constraint. And since it's an equality constraint, it's not a convex problem anymore, because you cannot draw a line from any point to on this quadratic constraint between any 2 points. You have to get out of the constraint, right? So it's not a convex problem anymore, and that's a problem. That's very annoying. So it turns out that if you just brute force try to optimize that, it usually doesn't work very well. The idea here is that we're going to exploit the structure that we have in this problem in order to find a simplification of the problem that works really well. So how do we do that? So as I said, the cross product, you can write the cross product is this way, right? The cross product between 2 terms in coordinates looks like this. And if you look at every term, it's basically the difference of 2 squares, right? So if you look at the difference of 2 products, so you can rewrite the product as the difference of 2 squares, right? I'm just playing with notations. I'm not doing anything special here. So right, AB is just the difference of 2 squares. Now I'm going to add 2 new variables to my problem, and I'm going to say that my new variable A bar is equal to 1 square, and the B bar is equal to another square. And then I basically make my original problem, my original constraint when I have A times B is just a linear constraint with my new variables, and my old variables is just basically a quadratic constraint. So what I'm saying is that now I need to make sure that this quadratic constraint is satisfied. This is the thing that is not quadratic, that is not convex. But now I can rewrite all my problems as quadratic equality constraints, and everything else is a linear problem, right? So how does it look like? It looks like this. This constraint is the one of this type, right? So I have the non-convex equality, which is thus the intersection of a convex inequality. X squared is smaller than y, right? It's everything that is above the curve. And a non-convex inequality, which is concave inequality, which is x squared is bigger than y, which is everything that is below the curve, right? So what you want is basically find the intersection of both, and if you do that, you're done. So this is true for this constraint shows up for the angular momentum with the cross product. It actually also shows that if you want to optimize time, so when you discretize the equations, time shows up as in a multiplicative way with the equations of motion of the system. So if you can relax the problem and solve it for this kind of problems, we can also use the same technique to actually optimize timing when you start to move on. If you want to optimize timing while you're moving. And this matters a lot because timing actually, depending on how much momentum you can build, the timing is going to decide whether or not you're able to cross certain terrains or not. So how do we relax this problem? So there's different ways. You could say I can take a linearization and then I try to solve it. It turns out if you just linearize the problem, it doesn't really work. You're not going to find a good solution. The other way, you can say I'm just going to take the convex inequality and try to solve this problem and assume it's good enough. But if you do that, you're going to end up in a region of the solution that is far away from the constraint. So this is not going to be physically correct either. The other thing that we're going to do is here is that we're going to build a trust region. So we can say, let's first solve we assume we just take the convex inequality and solve the problem, right? So this we can do really fast. It's easy, right? We have a linear constraint. We have a quadratic constraint here. So you have a second order program. You can solve it. We know how to do that. So you can solve this problem. Now the sixth thing is that now we're going to build a trust region by just taking the previous solution, taking an approximation, and building a trust region around this solution to try to push the solution now in a smaller region that is not convex, right? Now we can resolve the problem in this trust region. It's again a convex problem because the region that I'm bounding it is convex. So I can still use a second order program, solve it, easy, and I get the new solution. And if I iterate, I can basically push the system to the boundary, and I basically can solve the problem completely, right? By solving a series of second order programs. I can do another thing. I can build a soft constraint. So I first solve my original the convex relaxation problem, and then I build soft constraints that are basically using this first solution. I can build a tangent to the curve, and then I can force my point to try to go to the boundary. And by doing that, you can really try to project as much as you can the solution, and you iteratively do that by making the constraint. So use that as a cost in your optimization, stronger and stronger until it's converging on the curve, right? That's it. So this is just playing a little bit with the geometry of the problem. So it turns out now we have two iterative methods to solve the problem, right? And each iteration solves a second order program. This is something we can do very easily. You can give it to any type of solver that can solve second order program. There's a lot of them out there, and they work really well. They're reliable, right? It's a technology that works. And then you get a solution to your problem. So what happens? So then suddenly you can start to solve problems that look like this. So this is the solutions when you solve this problem. So solving the alternative optimization and using the dynamic optimizer, we use the series of second order programs to solve them. And this is what happens. So for the selection of the contacts, here we use a mixed integer program. So you can mix the second order program with the mixed integer to actually not only decide how the center of mass moves, but decide where you put your hands at the same time. And this works really well. So you can do this kind of motions. What is very cool is that all of these motions, they're optimized in seconds, in less than seconds. So if you look at the time that it takes to do the dynamic optimization for one of these motion, for a motion that is a length of 10 seconds, we take less than a second to optimize, right? And this is for two types of motion, and motion that is 12 seconds long, it takes a second to optimize. If you start to optimize for time, since we had a lot of variables, it's a bit slower, but it's still faster than the length of the thing that you want to optimize. So for a 10-second motion, it takes roughly 5 seconds to optimize. And what is interesting is here, this is the average time that it takes, whether if you optimize time and if you don't optimize time. So if you don't optimize the timing, it's a bit faster. But you see that it grows with the number of time steps, so the number of the length of your receding horizon, right? The growth, typically the growth is going to be cube, but the way that we do it, the growth actually is not cube, it's linear for the number of time steps, for time optimization, and for the amount of optimization. In this case, it doesn't grow. If you start to add a lot of time steps, you're going to see that the curves start to go up, but it's linear. We have a linear relationship, right? Which is nice, right? Because in general, you don't really care about optimizing a 10-second long trajectory. You care about optimizing maybe a 1-second long trajectory, and this you can do in real time. So that's great. Now we have a solution that can compute full body dynamically feasible motions. Yeah, you had a question?
In the videos, I was seeing things like the hands passing through obstacles and things like that. just or penetrating the blocks or things like that in the videos that you were showing.
Yeah.
How is that addressed in this framework in terms of making sure that these plans that are generated out of the optimizer are actually consistent with penetration constraints?
So that's a very good question. So there's two things in the video that you see. There's actually a visual artifact. It's just that the rendering doesn't match the exactly. So when it goes in contact, if you see that it goes inside, it's because these are plans that I'm showing you. It's just a visual. So it is at the contact that you want. So this is fine. The other thing is that if you have obstacles, we are not, in the kinematic optimizer, we are not tackling obstacles in what we're showing. You could add obstacle avoidance if you have a kinetic optimizer that can deal with obstacles. Here we use a cost on the obstacle. So we try to stay away from the obstacle, but it's not ideal, right? You should use a smarter planner for that. We are basically doing inverse kinematics for the kinematic optimization, right? You should do something smarter than that. We cared about the dynamic part of it, so we haven't really done much on that. But that's a very good question. We should do that. Now the question, so I showed you plans, it's great, right? The question you could say, okay, but does it work on a robot, right? Because we optimize these things, we rely on these very precise models. You assume that you know the models, usually you don't know the models, right? And even if you do system modification, usually in my experience, it's annoying and you're never, it's never exact. So we tried it, so we build actually a small quadruped. Robot that is it's an interesting robot. It's just repeated prototype, so it's just 3D printed, nothing fancy. We use brushless motors, so we have a very low gear ratio, so we can really do force control in a nice way. We actually measure the impedance relation you can get at the end effector when you control the current at the joint. And it turns out we have a nice linear relation, so we can really do force control in a nice way. So we took these plans. We computed two types of plan. We computed a plan to ask the robot to go from here and jump to go further. So it's really a dynamic motion, right? And then we use an impedance controller that just tries to move the center of mass and computes the length of the leg. And then we run it. And this is a result we did like 2 weeks ago, so it's very new, but it works, right? So we can actually, the plans we compute, they are feasible. And you can really execute them on the robot, which was kind of, I don't know, I found this very exciting, but it's, I didn't think it was going to work that easy for this robot. You could argue, okay, this is a smaller robot, it's much easier than to work with a humanoid, but actually there was no tweak in the plan, right? We took the plan, we put it on the robot, we run it, and it actually does work. So the dynamic plan makes sense, right? It's not completely off. Now you can see there's a lot of things, right, that maybe you don't like. The way the impact is done is not very nicely controlled. There's a lot of work that you can do into regulating what kind of impedance you want to have the legs. So this is work we're currently doing now. But the plans, they make sense, and it makes sense to plan in this way, right? So that's that was the first thing we managed to do that's the first robot we tried this thing on, and it seems to do something reasonable. All right, so that was for the part of say, let's use models, and then we optimize the hell out of that, right? And it's nice. It's nice up to some limit, right? So if you start to do very complicated interaction tasks, if you start to do like sliding, if you start to sleep and things like that, these models that I showed you, so the models we always assume fixed contact, so we assume you don't sleep. If you start to sleep, you start to do other things, it's much more difficult to deal with. So one other thing we're doing in the lab is say, can we actually learn directly those things from data, right? Is it possible to learn this? And another thing that we're interested in is say, here I need to plan a trajectory, and then I assume that I can follow it. And if I want to do this in a model predictive control way, I assume that I can plan this thing in real time, right? So I can replan hopefully at every 10 or 50 milliseconds, right? So it's very, very expensive. Another thing is like, can we use that somehow to learn a policy that will map any state to a desired motion, such that I don't have to replan the thing, right? Because what I replan is always almost the same thing, right? So if I could just store that, well, in this case in a neural network, maybe I can do something that can generalize and I don't have to replan all the time. So we started to look into these two things, and we were interested in a task that has very high impact dynamics, and see if you can do that. So that was a previous version of the quadruped. We had just one leg, so we started to do that with one leg, and say, can I learn how to hop? And in addition to that, as I said, we're going to put this in neural network. We didn't want to have something we don't understand. So we wanted to find the structure such that we can actually understand what this thing has learned in terms of physical properties of the system. So typically what I care about is what kind of impedance it wants to regulate. So what we did is that you start a trajectory, you start something, you learn a local dynamic model. So you get a trajectory, so you start with initial guess. You try this on the robot or in your simulator. You get a trajectory. From the trajectory, you learn local linear models. Once you have local linear models, you do iterative iLQR. So you basically take your linear models, you do a backward pass on that, you get an update on your control, you reintegrate forward, you get an update on your trajectory, and you keep doing that back and forth until it's converging. And then you have basically a locally optimal plan. So you have a locally optimal control and a locally optimal desired trajectory to solve your problem. Yeah? And then the idea is that you can use some of these solutions. So not only the trajectories, but also the full control law. So you have a locally optimal stabilizer that comes from your feedback gains, right? Can you learn that and integrate that into a neural network policy to be able to generalize? So if you learn a few of them, can you basically learn something that can interpolate between that, right? That was the idea. The other idea is that instead of making, so these things are trajectories, so they're time-based, right? So it means that if you want to, if something happens, you need to rechange your time. You need to replan, right? Or you need to readjust the timing. If you make things state-based, so you learn something that maps the states to the control, then you don't have to have the notion of timing anymore. It just depends on the actual state of the system, which matters a lot, especially for locomotion. State-based things tends to be nice because you don't have to deal with the following a trajectory. You just look at the state of the system. It tells you what you need to do next. So what people would do, so I don't know how much so people, usually in people using reinforcement learning, they have a state and they basically learn a control and it doesn't matter what it means and you just send this on a robot and you hope it works, right? So, and we do that also. So we said, let's not do that. Here, there's a lot of structure, right? When you optimize something, you've learned a model, so you have a model, you optimize something, you have a lot of structure in your problem. So I would say, can I learn something else? And what I want to learn is I want to learn a desired trajectory, a feedback gain, and a feed-forward command, right? So instead of learning an arbitrary output, I don't understand what it is, what I want to learn is basically the control law, right? So this is the state of my system, and I want to learn the desired motion that I want to do. I want to learn the gains. In the gains, it directly tells me what is the impedance that I want to have at the leg, right? Which is really nice when you do locomotion because it tells you whether or not you're trying to be stiff, which, to me makes a lot of sense if you want to work with contacts. And the feed-forward torque is basically what is your model telling you should do, assuming that everything is perfect, right? And so we did that, and it works. So for a hopper, it's really nice, it works. And what is really nice, what I want to show you here is that what we can learn when you modulate the environment is that this is the gain output for one dimension. This is for the hip and for the knee, and this is the gain that is directly related to the joint, right? You can learn the impedance regulation, right? So you can see here that, for example, here it's stiffen up when it starts to take off, and then it basically predicts that you need to decrease your impedance before there should be a contact, but there's no contact that happens, so it stiffens up again, and then it goes down again in compliance when there's a contact, showing that we really learn something that is related to the contact interaction, right? So the regulation of impedance here is really related to the fact that there is contact on it. So we can really learn something that I find is meaningful to some extent. What is interesting with that is that, so we tried this, so here we optimize two types of iLQR policies, and then we learn the problem is that if you have this time-based iLQR policies, if you change the environment, it doesn't work anymore, right? But now with the neural network that you've learned that is state-based, as you move the environment, this thing is able to deal with the change of environment. So this is in simulation, but this is also working on a robot. So this is an example where basically we only learn two trajectories from a flat ground, learn the neural network from that, and this thing was able to generalize to variations of the environment, right? So this is actually, this is kind of nice. But this is not the end of the story, right? This is a simple problem. Hopping is interesting, it's dynamic, right? It's very dynamic impact. But this is not solving a very complicated task. Again, the environment is rather simple, right? We're not varying the environment a lot. And the other thing is that we assume that we can learn this local model easily. It turns out that to learn this local model easily, you need to have a good guess of what is a trajectory you should try that is going to give you information, right? If you try the first trajectory that gives you zero information about the dynamics, you're not learning anything. Then you synthesize a controller that doesn't do anything, and basically you're stuck, right? So you're not going to be able to do anything. So the last the more recent thing we've been looking at is say, can I design systems that not only try to optimally learn the dynamics, try to optimize a control to do a certain task given this knowledge that we've learned, but use the knowledge that there's things we don't know about the model to try to explore a bit more, right? So you don't only want to exploit what you've learned, but you want to try to say, oh, there's this part I don't know anything, there's a lot of uncertainty in this part of the model, can I go there and explore what's going on? So this is a work I've done, it's in collaboration with people at Facebook, Franziska Meyer and Akshay Rai, and Sarah is a PhD student in my lab. And so we started to look at this, we called that curious iLQR. So actually it's this idea, can I do iLQR, but explore things I don't know at the same time. And so what does it mean? So as I said, you need to have good data to learn a model, right? So how can we explore parts that are uncertain in the environment such that I can gain useful information to improve my model in order to improve my control, right? Because at the end of the day, the only thing that I care about is whether or not I can control my system. So can I do that? And what we would like to do is that we would like to learn a probabilistic dynamic model that contains not only an approximation of my dynamics, but that also contains the uncertainty that I have about whether or not I've learned something useful, right? So you can do that, for example, using Gaussian processes. You can not only learn the regression, but you can also learn, because it's a Bayesian approach, you get associated to that a measure of uncertainty of whether or not what your guess is correct or what might be the variance that are associated to that, right? And from that, we want to design a controller that is not only try to optimize a certain task based on this model, but is going to take into account the variance in order to maybe explore parts of the dynamics that are not known very well right now. And in order to do that, we're going to use risk-sensitive control because it has a very nice result that makes it algorithmically very, very nice to optimize. So I don't know how much you know about risk-sensitive control, but the idea of risk-sensitive control is actually very, very simple. You start with you have a process model, so dynamics, right? So in this case, it's a stochastic process. So the red part is noise, arbitrary. So usually you assume it's Gaussian to be able to derive anything by hand. We have an objective function, right? That's what we want to optimize. Typically in the stochastic dynamics, you don't want to optimize the objective function. You want to optimize the expectation of the objective function, right? So that's the typical thing, right? And if you do that, and if you have a linear system and a quadratic cost, and you want to minimize the expectation of the objective function, you end up doing LQG, right? So you will have a Kalman filter and an LQR, and that's the optimal solution. Now the thing that you can do is that instead of optimizing the expectation of the cost, if you optimize you want to optimize not only the expectation of the cost, but you want to have a notion of the variance that you will have associated to that, right? Because having a very low cost is great, but if a small epsilon change in that leads to a disaster, is not good. So you want to not only factor in the expectation, but also what is give a cost to the variance that you will have in your cost. And there's a very nice way to do that. There's basically a very old technique from Jacobson. Instead of minimizing expectation, you minimize the expectation of the exponential of the cost with the parameter sigma. And if you look at the series expansion of that, at the log of this term, it turns out that what shows up is that you will basically minimize the expectation of the cost plus sigma divided by 2 times the variance of the cost plus then you have a series, so you have the skewness and all the other moments of the distribution, right? So what does it tell you is that if you have now, so forget about the higher order terms, what it means is that you try to minimize the cost, and if sigma is positive, you penalize controls and behaviors that have high variance, right? So it means that you try to be safe, so it's called risk averse. It means you try to not take any risk, you try to have solutions that have very low variance. If you do it the other way around, and that's what we're going to do in our case, what you do is that things that have high variance, it's good. So we're going to try to favor things that have a high variance. Why is it interesting in our case? Because the variance is going to come from our model. So if our model has a high uncertainty, I'm going to try to seek to go towards places that have high uncertainty to reduce it, right? So as I said, if sigma is positive, we're going to favor high variance cost. And it means that, positive. No, negative, I messed it up. Yeah, sorry. Negative, it favors high variance cost, and this is what we want to do. So that's the other way around. And the thing I didn't say is that if you have a linear dynamics and a quadratic cost, you can actually find Righetti equations type thing that can solve this problem. So it's the same as solving LQR, but with a different type of Righetti equation that basically factor in the covariance associated to the noise. And then if you don't have a linear model, but you can have a series of linear models, then you can do iLQR, but the version that is taking into account the risk. So basically you do iLQR with the new Righetti equations, and it does the same thing, and then you can factor in the risk into this problem. So that's what we do. So here we do that with the manipulator. We're not doing with contact yet. The idea is that we take a manipulator, we want to reach a certain target. There's no model, so we don't know anything. We start with the first guess. You collect data, you feed a Gaussian process that tries to predict basically the next state. So you try to learn the dynamic model, right, with the Gaussian process. What you get is that at every step, what you get is a Gaussian distribution for the prediction, right? So you can linearize the system and get the Gaussian distribution. So it gives you the mean, condition on the current state, the mean for the next state, condition on the current state, and the control that you decide. So it's a linear model pretty much. And then you have the covariance, right? So you can use this covariance matrix into the iLQR backward pass to do the risk-sensitive control. So what we do here is that we basically do risk-sensitive, so risk-seeking iLQR, computing a policy based on this model. And this, we get basically a feedback gain, right, of an optimal control law that now is going to not only try to achieve the desired task, so minimize the cost, but also try to seek areas that have high variance, which is areas that have a high variance because the model is not very well known, right? So we're trying to balance the exploration and the exploitation, if you will. And what is nice is it turns out that by doing that, you learn the model much faster and you can actually generalize better after very few trials. So this is an example where you try, so this is an example of a reaching task after several iterations. So there's the first iteration, second, third, and fourth iteration, so we try. We tried with the curious one is this risk-seeking iLQR. So you learn the dynamics, do LQR, run it, do dynamics, do LQR, run it, and you do that 4 times. In orange, that's the curious one. In blue, that's a normal, so you just do LQR, you don't include the risk part. And this is the end-effector trajectory in 2D, right? So for the curious and sorry, so that's when you first learn. Sorry, I messed up these 2 graphs. That's the first one that we do, so the thing tries to learn. And you see there's a lot of variance the first time, then it learns a bit better and converge that. The normal one converges a bit faster because it doesn't really explore anything. And then you can learn how to reach the target. But now when you give it a new target, the normal one is still going to have to explore because it needs to learn in a different part of the space that it's never seen before. While the curious one already knows what to do because it learned that in the first iteration, right? So you can generalize, and it shows that basically the model that was learned here from the curious one was richer, and you're able to learn to basically generalize to a different task without having to relearn anything in between, right? Because the model was good. So we tried this on the robot. So this was done at Facebook. And this is what happens. So here the comparison is the 2 approach, one using the risk-sensitive part and the one just doing normal iLQR, fitting a Gaussian model from scratch, right? So the only data that you see is the data that you see in the video. We don't do anything else before. So the first time it's pretty bad, right? It doesn't reach the target. The target is the green, both for the curious and the normal robot. The second time is a bit better already. So it learned a notion of the dynamics, at least locally, that starts to be good. And after 3 iterations, so we send torques directly to the robot, right? So so we really learn the dynamic model. You can see the curious has started to explore part of the space that has nothing to do with the task because it has a high variance, right? But eventually it managed to reach. Then it reached the target. In this case, with a lower error than the other one. So the error is not there's still some error, but it's another robot you can control it really precisely anyway. But what's interesting is that now you change the target and you give it another target and you see what happens. And what is nice is in this case, so there's no more learning here. We just see how it can generalize to other targets. And it turns out that with the curious one, with the same number of iterations, right, we learn a much better model so we can actually generalize to things we've never seen. Which is kind of nice. So we hope that by doing that, we will be able to learn more efficiently on the robot, because what we care is to really be able to apply these techniques on real robots, right? All right, so that's the three things. So I showed you three different things. I showed you, say, what if I use my models, my Newton-Euler equations, and I try to optimize things? Can I do that really fast? And what I thought was interesting, we found in this work, is that there's a lot of structure in these equations. If you exploit them well, you can actually get really, really fast, and you can have guarantees in what you get. Then you say, can we learn models from data and start to do more complicated impact problems? And we can, but we still need to do more work. I think it's not sufficient. And they say, well, if you want to learn these models, can you do it in a way that basically explore in a smarter way and maybe a bit smart with how you generate data, such that you can learn these things faster? And we're really scratching the beginning of that, so there's still a lot of work to be done in that, but I think that's nice. And hopefully what we can do is that at the end, we're going to do basically a mixture of these two things together, so that we can really have robots that can not only learn, but use all the knowledge we have from physics to optimize. As you can imagine, I'm not the only one who's done that. Actually, the work has been done by everyone else, pretty much. So I would like to thank all the people in my team and the people who sponsor our research. Thank you.